Good afternoon, everyone. Thanks for coming for our 8th seminar in the semester. Our speaker today is Abdullah. Uh, Abdullah is a PhD candidate in the Bradley Department of Electrical Engineering at Virginia Tech. He got his bachelor's in computer engineering from Arab Academy of Science and Technology in 2003, and he worked as a teaching assistant and as an assistant lecturer till 2009. He joined Virginia He got his master's in computer engineering from Virginia Tech in 2007 before joining wireless at VT in fall 2009 for his PhD. His research interests include wireless networks, opportunistic spectrum access, multimedia networking, and his current research focuses on optimizing HTTP-based adaptive video streaming over wireless networks. He worked as a graduate wireless intern at Intel in 2011 and Broadcom in 2013, and is a peer reviewer for several conferences and IEEE journals and magazines. So, good luck. Today we'll be talking about the spectrum observatory that they have built here at Virginia Tech. Cool.
Good afternoon, everyone. Today we'll talk about a network of spectrum observatories that are scattered between several locations in US and Finland. We'll start with a quick introduction, then we will talk about this specific project that includes all these observatories. Then we will focus on the system installed here in Virginia Tech, taking a quick look at the spectrum occupancies here in Blacksburg. Then I will discuss some of the correlation studies that we carried on over the last few months on the spectrum usage with respect to the human events within the town of Blacksburg. So first, why we need to observe the spectrum. Some trivial reasons is that basically we need to use this data to create prediction models for improving spectrum sensing or spectrum decision making or the spectrum sharing and mobility processes. Also, regulators are interested to keep monitoring what's going on. Some previous significant campaigns were done by the NTIA and by the Shared Spectrum Company, as well as the Aachen University. One of the most spectacular spectrum campaign actually is done by Illinois Institute of Technology, and they are our partner now. And they have data that goes back into scanning the spectrum in Chicago since 2005 continuously. They didn't skip a single day. However, this long-term data is not actually made available for public access, and this is one of the goals of this new project. We now are a part of this global RF spectrum opportunity project, which got its fund from the wireless innovation between US and Finland program. And this program is funded by both NSF and the Agency of Innovation in Finland called TEKIS. The project includes two universities in US, which is Illinois Institute of Technology and we here at Virginia Tech, presented by Dr. McKenzie, and three locations in Finland. Turku University, University of Oulu, and VTT Technical Research Center. The goal is to deploy several RF spectrum setups, then make this data available to the research community, then mining all this long-term data using different statistical methods and big data mining techniques, in addition to develop some prediction models. These are the list of collaborators in the project. It's a big project, especially the site in Illinois. So many contributors over there. The idea is that we collect the data in different sites in US and Finland, then just buffer these data for a sequence of like few weeks or a few months while the big part that work as the repository to keep everything is the big servers in IIT in Chicago. So we have the same system, duplicated in the sites in Turku. It's the same system same hardware that is used here in Virginia Tech, same hardware that is used in IIT. And everyone buffer his sites, then the data is to be pushed to the main servers in IIT. So the locations include Turku, and Turku has two systems over there. One that is just a fixed system over one of the building of the institute. And they have a backpack system that they can just go to, let's say, a music concert in the middle of the town. Someone just standing there with the backpack in his back, scanning the spectrum for 2 hours before, 2 hours during the event, 2 hours after, and then we can look at what kind of relations and correlation we can find. In Chicago, they have two fixed sites in like the Harbor Point in Chicago and the IIT tower over there, in addition to a mobile system that is actually can be installed on a van and they just drive all around. And they used some sort of like personal carry version from this before so that they can collect some data from football team, their White Sox team. Oh, sorry, baseball. Now I understand more about the data. So now this is our site here in Blacksburg. This thing is actually installed on the roof of Whittemore, which no one has access for it except us. And Dr. Volk has a similar scanner next to us. We use a hardware made by a UK-based company called CFRS. The system is called RFEye node. And it's basically an embedded Linux system box. It's kind of a black box, even though some of the API is programmable, but it's still kind of black box, not like using USRB, for example. We scan everything between 30 megahertz to 6 gigahertz. And then push our data to hard disks that are connected to the Virginia Tech LAN. The company is providing actually a lot of other services with this hardware, but we just using the minimum since we are not interested in the other things. But one of their most interesting system is actually the live streaming data application, which similar to what you can do with some USRB software. These are the system features. It has a GPS antenna and receiver for basically time stamping the data, and this is what we are using to time stamp our data. This is just the internal layout. But one of the most interesting feature in the system is actually the HTTP interface. You can do everything on the HTTP, and you can also get live stream of data over a UDP-based connection. That you can, instead of just storing the data like what we do on a hard disk connected to the LAN, by copying from the local storage of the node, you can actually get the scanned data immediately over a UDP stream. Currently, we are running two spectrum scanning plan according to what the project partners agree on. We have a high accuracy plan that just take 3 seconds interval over the most important bands. And we have another low resolution plan that is run on a sweep interval of 20 seconds. Now, I will take a look at the spectrum status here in Blacksburg by just focusing on some of the most important bands. This is a color-coded power, let's call it a spectrogram for the 700 megahertz band in Blacksburg. And this is actually mainly the LTE usage for US Cellular, AT&T, and Verizon. On the left side is actually the uplinks. The one that has, of course, the very reddish color, this is the downlinks. And we can see how busy actually this band obviously in the region here. This is the average power over every single band that we scan over. And I'm illustrating this now because we will use the same figures for comparison when we are talking about the correlation with human events. This is the PCS band. On the left is the downlinks, and on the right are the uplinks. And this is, by the way, over a period of 24 hours, all of these graphs. And this is the average. Here's the AWS.
Well, why are we seeing so much uplink and so little downlink?
Sorry?
It seems backwards.
Oh, yep, sorry. Yep, this is reversed. The left, this should be the uplinks. This is downlinks. Typo. Okay. Yep. Reverse. So this one should be the uplink, this one should be the downlink. So this is the downlink for the AWS, Verizon, and T-Mobile, and we can actually maybe kind of see that some bands, even though they are assigned or like licensed to certain service provider, but they are not actually used. Like this band that's supposed to be for Intel's, but even though it should be a downlink, but it's obviously not being used. This is the uplinks for the AWS. Now let's talk about the correlation with human activities. Basically, if we look at it from a timing perspective, we want to look at, let's say, a micro level and macro level. Micro level, we can look at the rush hours per day, maybe the time between noon and 5 p.m. This is going to be the highest activities. Or if we got closer to the downtown after 5 p.m., then maybe the activities will increase next to that area after 5 p.m., maybe until 10 p.m. or something. But since we are here in Blacksburg, one of the most interesting things for us was to see that what's happening in the most important events in Blacksburg, which is basically the football home games. And we started to look at this, and since most of these games, home games, are actually on Saturday, so we started to look at the Saturday, regular Saturdays versus the Saturdays when we have a Virginia Tech football home game. Then we started to look at regular weekends or regular Saturdays versus significant different Saturdays, like let's say the fall break when everyone already left the town. So let's start with the data we collected over the home games. This is kind of a schedule that we made for the home games. And let's take a look now at September 6th when there was no game versus September 20 when the game was like Western Michigan. And from the data that we got from the VT Sports website, this was supposed to be the most game that had actually attendees in the stadium that day. So looking at the land mobile band in 450 to 460, we can see that in total, the average is always higher in the game day over almost all bands. Some bands that are almost were not used at all had some peaks on that. If we, and this band is mainly used by VT Police Department, the Blacksburg Police Department, Virginia Tech campus services like the parking services, the BT bus, and actually whatever we will do, I will show later, was mainly focusing on the BT bus channels. This is the 460, 470, which is the rest of the band. Less significant, but still you can see that the average power is much higher.
But still, the difference is not as much as one would expect, right? If this was such a significant event that there was a record-breaking attendance, then one would expect that the difference you see is much higher. Is it because the observation point is a little away from the stadium?
Definitely, this is like the distance is making a great difference in what we receive in terms of the power. Also, I think that our location, the big difference is coming from the tailgate period, not from the game time. For example, if the game is between like 6 and 8, no, it's not within this hour. It's actually the extreme is in the tailgate, since the node is just in front of the very street parking.
And at the same time, I think it's, if let's say I go and watch a game, I will be watching the game and not making phone calls there, right? Or I would really be watching videos there. So it's also, you have to keep in mind, is it really the right setup where the observation should be made?
Actually, the correlation that we saw in Chicago data for the baseball match is...
Baseball is another thing.
Actually, they were looking at the uplinks, and obviously everyone was doing something.
Yeah, you can't survive a baseball game without
The data that you collected was for not the cellular data, right? You said it is of the police and the public.
Yeah, I'm moving now to the cellular data on the same day. Yes, it's coming on the next slide. So the next slide now is the 7 megahertz LTE downlink. And there is a difference. I don't want to call it obvious, but there is enough difference to be investigated. These bands are basically US Cellular, AT&T, and Verizon. These are the downlinks. And if we look at the AWS, okay, now these were basically the games, like September 20 and September 6. For the AWS on these days, we didn't see that much difference. But when we move to a day like the regular weekend of October 4th versus the full break, October 11, when almost the town is like ghost town, almost everyone left, now we can see something on the AWS. However, we can see it basically in Verizon. We cannot see that much different in T-Mobile. Is it a technology-wise? This is still something to kind of investigate. When we move to the uplinks, we can even
Can you go back?
Sure.
So here the thing is that you average, right?
Yes.
So an LTE band has lots of control signals, download, lots of reference signals, and those are the ones that don't change.
Okay. And this explains why.
Yeah, you cannot capture the action.
Okay. These are the average power actually, but when we look even at the whisker plot, there is obvious difference between these days. I didn't include this here, but with the whisker plot, it shows you that the range is dramatically moving.
I think you would gain more insight if you look at the uplink. Because the uplink, there's more user signaling than control signaling. And the downlink, you have these specific control signals that are always there, especially in the middle of the band. they're always there. So you always find things.
Actually, I think I completely agree with you because the whisker plot in the upper links is way significant than the downlink. Like even though the whisker plot in the downlink is giving much more information than the average, but in the upper link, actually now I'm actually using it more than the average. I'm just using the average here for illustration. But for the upper link, it shows like, so this is the uplink, and even within the average, we can see the difference. And as I said, with the whisker plots, we can see much more. So the question now is, can we actually learn this relation? Can we detect the differences? And later we can predict the events based on it. So we started to think about how to quantify this or how to look at this. And I started doing using clustering for this, basically using Gaussian mixture models, since the histogram looks more like Gaussian mixture. So I thought about using Gaussian mixture models. Gaussian mixture models, for those who are not familiar with, it's basically a soft clustering version from the k-means. When the k-means run, the k-means assuming that the covariance between the different components or the different clusters is following an identity matrix. While with the Gaussian mixture model, the learning algorithms is actually updating the covariance while it's running, so it's not assuming that it's identical and between the different components. Basically, the output that you get from the Gaussian mixture model is just the vector of means of every component and the covariances, in addition to what we call it the component's weight, which is how much this component is contributing to the overall probability density function. The algorithm is well known as the expectation maximization algorithm. You have an initialization step, and then you iterate by evaluating the membership weights, which is also called the responsibility for each data point from those that you train as a batch training, not as a sequence training. Then you do the maximization step by updating the component, then evaluate the likelihood and check for the convergence condition that you have in the algorithm. But the challenge is, when you start, is how many components you actually assume that they are there. Of course, as many components as you add, as the model should be better matching or fitting the data set that you have. But if you keep increasing the number of components, the K, you end up in overtraining or overfitting actually with the data. So one way to solve this, and like there are several metrics to use to evaluate which model is better, is to use, in my case, I used the Akaike information criterion and in addition to the cell-hood values test. And the Akaike information criterion, in a quick summary, it's basically just like kind of penalize the log likelihood. So, okay, now you can get better maximum likelihood if you increase the number of components, but I will penalize whenever you increase the number of parameters. So there will be like a trade-off between how many parameters you can add versus this penalty function that it's applying in evaluating. So basically, when you apply the AIC, you should choose the model that gives you, the mixture model that gives you the minimum AIC value. In similar way, the way the cell-hood values test is working is that, and it's people who are more familiar with the k-means algorithm, they know more about the cell-hood values, that it's basically measure how similar the relativity between how similar each data point to the cluster it's already assigned to, or the component is already assigned to, versus how dissimilar it is comparing to the closest neighbor cluster. And it gives you a value between -1 and 1. And if the value is negative, it's actually an indication that this data point should have been assigned to different cluster. So your average of absolute values should be always positive. If it's negative, this means that the clustering result is really bad. It should stay positive. And most of the values has to be actually positive. So when you evaluate different models, you will choose the model that gives you the highest average value, as well as the minimum numbers that is actually fall below zeros. So we just take one example by picking one of the channels on the game day versus the no game day. And we did this basically over a channel from that is assigned to the BT bus services. And with applying the GMM, I ended up having lower values with k = 3, and it's matching the values also shown by the Sulhut figures, is that the less number, this is K2, 2 components, 3 components, 4, 5, 6, 7, and the minimum number of values that would go below 0 is the one taking place with number of components 3, which is matching the AIC. Now, this figure illustrates the detection accuracy for more than, like, for several channels within the same band. All of them are used by the BT bus. The x-axis is basically the detection threshold. Like, each component now has its estimated mean, and we move the mean right and left with a certain delta value, okay? And we check for the detection accuracy whenever we go farther left or farther right. So the channel that I actually showed in the previous figure is actually the channel marked by the square red. And the rest, the remaining channels from the same band are the other ones. And we can see that we can tell with very high accuracy, I would say, which source this values is coming from. So this is just preliminary results for detection, and we are not detecting a game day versus no game day. This is the sources for a game day and the sources in a non-game day. The ongoing work that I'm working on now is that, okay, let's now take each component that are detected on game day versus non-game day, and it's like each component on the no game day and its corresponding component in the non-game day, and look farther inside each of these distributions, so that I can tell later when you give me a stream of data if this is matching a game or no game, not just which source. And what I'm using for this now is self-organizing map neural network. The good thing about using the SOM neural network is that you can actually put on top of it any model. So with this GMM model, I'm using the mean values as the starting values to train my SOM neural network nodes. And then I can treat every distribution separately and look at what points within this distribution can be detected as no game or game. This is one thing. One more thing that I'm doing is that I'm looking at the timing relationship. Basically involving some hidden Markov model to look at the timing relationship so that I'm not only considering the power values, but the relation between these values and its arriving time. This is everything I had for today. Question?
Sahil, So what is this value of tolerance exactly?
You have the detection rate, like the mean of the component at a certain value. And what I'm doing here is that I'm just shifting the detection. So instead of that, saying that, usually what we do is that I will take the mean, and then I will add a confidence interval and see like how far with how multiple of the standard deviation I should go beyond the mean. What I'm doing here is that, okay, let's add a delta to this typical way of finding the detection threshold. I'm doing this basically because if we are using this to predict the on-off state, like to see like if the channel busy or not, we actually don't have the reference. Like we don't have the reference for these data. So what should we do in this case is we add a tolerance and look at the accuracy under the tolerance, and also with another curve that I didn't actually include here is the response operating characteristic curve, where like by moving the same tolerance, you check the false positive rate versus the true positive rate. So both of them, this curve and the ROC curve together, should tell you how accurate actually the classifier is working, given that we don't have a reference to refer to, saying that, yes, it should have been this detection ratio because the binary values of the on-off state should be like that.
Is there any reason to believe that this should be a symmetric curve around some value? Because what you're trying to do is you're moving it around some detected mean. But the way this curve behaves is this is not symmetric. This doesn't seem like symmetric, although we don't really have the second part. We can see it's more like it's going to taper off slowly on the right-hand side.
It's not symmetric. Like it actually goes on the other side much slower.
Which means there is some bias towards having smaller values.
Why does it go down? If your tolerance is 20 dB, you are always detecting it properly. It should actually flatten out. Right?
Sorry, say that again?
It should flatten out at 100%. It should not come down. Why does it come down? You said the other side it slowly comes down.
It's not going down as fast as
Why
the
does
left
it
side.
even come down?
If we are sure about what is actually the detection value in the channel, then yes, around this value it should be symmetric.
No, your tolerance is 20 dB, the x-axis. So you're telling that within 20 dB and whatever is there, I'll be able to detect it. So if your tolerance increases, you will always detect something. So it's always 100% detection ratio.
No, but if you go by that logic, then what do you mean by a tolerance of minus 20 dB? So here is a
Oh, so that's why it's going low, right? With minus 20 dB, if you want to detect a signal A versus signal B, you can only detect it 40% of the time. So it goes to 0. This side it goes to 0, and that side it should go to 1. It doesn't fall. I mean, regular.
But this is not one source.
Doesn't matter. You consider all your GMMs, all the threshold, maybe 100 dB is your overall threshold. So that includes all your GMMs. You are detecting something in this 100 dB.
So how are you adding this tolerance? So I think that is the key there. So how are you using this in the mathematical expression? Is it some value that you add to your threshold?
Yes.
Then what he's saying should be true, because you are basically making your threshold higher and higher, right? Depending upon how you use the tolerance. So it should basically go to 1 and just remain there after some time.
Sure.
So you're finding basically some CCDF type of product. So you're finding probability of X bigger than some T, right? And then you are adding some value to T. So that's how it is operating. So on one side, depending upon how you look at it, on one side this should go to 1. probability of, let's say you have a positive random variable, probability of that random variable being greater than 0 is always going to be 1. So depending upon what tolerance you have.
I think that the total will always go to 1, but it's not. I think by looking at the ROC, we can tell if there's something wrong with this or not. But the ROC is like, it's following the normal ROC behavior. Like you reach a 1 and then you saturate, and then the false positive keep increasing,
Right.
and true positive is not moving any farther.
And this will be symmetric when your JMMs are equally weighted out.
I think this should be symmetric, right?
Like what?
During the definition that we see.
It depends on the JMMs.
If he's adding a value,
It depends on how the JMMs are weighted, the relative variances and things.
Even if I'm moving only 1 GMM at a time.
Within 1 GMM, it should be symmetric, yes. If you're trying to detect all of them together, then it should not be symmetric.
This is the average over all of them.
Yeah, so that's what one is symmetric.
Okay. Any further questions?
Speaker less than